So now we will just revert back to this quantity that is in the weak inversion region. Okay, so we know that the GM over ID term gets saturated whenever I deal inside the weaker inversion region. Okay, and because of this, what happens is that I end up having a kind of exponential graph. Okay, now what I said is that I have an exponential graph over here, but this exponential graph or the current that I have here is not normally not visible when I try to plot along the normal axis. Okay, so now instead of plotting this ID in a normal axis, I'm trying to convert this ID in a logarithmic axis. Okay, so what I'm trying to do is that I'm trying to plot a y-axis in terms of logarithmic scale. Okay, so due to which you could see that there exists a kind of slope. Okay, so there is a line, and this line actually exhibit a slope. Now what is this slope conveys us? So what I said at the beginning is that the GM over ID is actually represents the slope of the logarithmic scale of the current ID, right? Yeah, so in this case, you could see that there is a slope that exists when I'm working in the weaker inversion, and because of which, when I try to read the slope value is constant throughout this entire region. Okay, throughout this entire region, the slope is constant, and due to which you could see that the constant value is getting reflected onto my GM over ID. Okay, so since because the slope is constant, we end up having a constant value of GM over ID when I'm working in the weaker inversion. Okay, and that is how it exponentially depends. Okay, now what we do next is to try to derive the current equation. Now, why does this current flows? What is the mechanism by which the current actually flows between the source and the drain is what we want to analyze right now. Now, when I look carefully here, it's nothing but it's an NMOS channel. And whenever I have a value of VGS that is less than VT, what happens is that it creates some sort of depletion region. Okay, but there is no charge carrier or the free carriers that exist between the source and the drain. Then you might wonder like how exactly then the current can flow between them, right? So I have to talk about the substrate medium that I have here. Okay, the type of substrate that I have is basically a p-type substrate for an NMOS transistor. Okay. Now clearly there exists an N-type material for the source and then a P-type material along the substrate and then again an N-type material for the drain. So clearly this is nothing but it's a kind of BJT, right? So it's nothing but it's an NPN transistor that I could see over here. Okay. So across this I could see there exists an NPN transistor, something like this, between the source and the drain. Okay, so the base of this BJT is actually getting connected to the gate terminal of our MOSFET. Okay, but this connection happens through some sort of dielectric medium. Okay, so you could see that there is a dielectric medium and you have a potential across this particular gate where this potential gate voltage is lesser than the value of VT. Okay, so obviously when you have this kind of setup, it actually end up creating some sort of an oxide capacitance, and also there is also one more layer that happens between the oxide and the substrate. We could see that there are depletion layer, and we know that these depletion layer are being created using immobile carriers. Okay, so these are ions, they are not supposed to move, so they can also be considered as a kind of oxide kind of material. Okay, so due to which we end up having two type of, maybe this is not COX, it is the C diffusion. Okay, so because of this layer, the diffusion immobile ions, okay, we have one more capacitance that is connected from this interface towards the body of our transistor. Okay, so that is what is being plotted. So now if we see that the gate is connected to the base of my BJT through some sort of capacitive divider network. Okay, so we have two type of capacitance between the gate and the body of our MOS structure. Okay, there are two capacitances that are there, and because of which we end up having this as a kind of setup. Okay, now if I know what is the value of VBE, the effective value of VBE, then it becomes easier to derive the current equation that flows between the source and the drain when I'm working in the weaker inversion. Okay, so due to which I use this capacitor divider formula to calculate the effective value of VBE here. Okay, so that is nothing but the VBE can be written as VGS into the capacitive divider network, which is written as COX divided by the summation of these two capacitances. Okay, so it's just a simple capacitive divider network formulae that I've used. Okay, and that I can step down this division as a kind of a ratio factor. Okay, so we call this N as a kind of slope factor. Okay, and in general, the factor n is quite higher than the value of 1. So this means that the effective voltage VBE that I have across this BJT is normally smaller than the voltage that I directly apply to the value of VGS. Okay, so in a way, I could write this drain current, however I've written down the collector current, the same way I can write down my drain current as well. Okay, that could be approximately closer to the saturation current. Okay, in this case, it is the off current that has been written, and it is exponentially related to the VBE. But we know that this VBE is stepped down by a factor of n. Okay, so that when I plug in here, I end up having a VGS divided by the slope factor times that of the thermal voltage UT. Okay, and normally when we look for a bulk MOSFET, okay, for any particular technology, the range of value this n varies from 1.2 to 1.1. But when you go for silicon on insulated technologies or FinFET technologies, the value of n is actually closer to the value of 1.1. Okay, now using this current equation, I just want to calculate GM over ID term. Okay, so in order to do that, I first have to perform a derivative on this current expression. And when I do so, we end up having a GM that is directly proportional to the value of ID. Okay, but they are being scaled down by a factor which is n times that of UT. So what does it mean? When I compare this this GM that I'm getting with the BJT, we have something like IC divided by the thermal voltage. Okay, whereas here the GM value is further stepped down by this factor n. So this means that the efficiency that I would get out of this MOSFET is less compared to the transistor efficiency that I would get in a BJT. Okay, so the transistor efficiency that we normally get in a BJT was quite higher, and the value is 1 upon UT, and that is equal to somewhere 38.5. And okay, so this is what we have seen in the previous slide. Okay, whereas in this case, this value is generally divided by the slope factor, and because of which the transistor efficiency that we normally get in the weaker inversion would range from 35 to 25. Okay, so if you are using something like a FinFET, then you can have a maximum transistor efficiency, whereas when you go for normal MOSFET technologies, then you may even get a maximum value of GM over ID that is closer to 25 as well. Okay, next we will see the use cases of this weaker inversion. Okay, in this case, first we'll look at the gain of this particular circuit. Okay, so we know that the gain can be written as GM times R out, and again the R out can be written as VA, which is nothing but the early voltage divided by the bias current of the circuit. Okay, so this bias current is right now the current that is defined in the weaker inversion. So whatever I'm trying to talk right now is with respect to the weaker inversion. Okay, and the graph on the right side plots for all, but I'm just concerned about the maximum gain that I would attain from this particular transistor. Okay, so clearly we could see that the gain clearly depends on this particular ratio. Correct. So the gain is proportional to GM over ID. Now we know that we would get a maximum GM over ID value only in which region? It is in the weaker inversion. Okay, and that is what we have seen till now. Okay, in the weaker inversion, I know that I will get a larger value of GM over ID. Okay, so generally you might tend to use this GM over ID to be large in order to have a very high gain. Okay, so in the case of a stronger inversion, this ID can be replaced with half Kn dash W by L, and when you try to substitute them, we would end up having something like twice the value of VA divided by VOV if you are trying to use this stronger inversion region and trying to adopt the square law model. Whereas when you try to adopt the sub-threshold model, then this ID can be replaced with ID that is approximately equal to e to the power of VGS divided by UT. Okay, yeah, so this is the current that I have used here, so that when I try to adopt, we end up having this as our gain. Okay, so clearly by making use of the square law model, I can predict the value of gain in the stronger inversion, and I can predict the value of gain in the weaker inversion. And now when we really compare these two values, assuming that the value of VA is constant, okay, so we will address this as well. Okay, so in this case, let us assume that the value of this VA is assumed to be constant. We know that the value of UT in general is quite small. Okay, And the value of VOE in general taken around like 1.1, even 1.2 is what generally people would take. Okay, so this means I am having a VOE value which is almost closer to 200 millivolt. Okay, and this is the least value that I can use. Okay, if you are using in that way, you would still get to know that the gain that you would achieve in the stronger inversion is small compared to the gain that you can achieve in the weaker inversion. Okay, so the same you could see over here as well. Okay, so here I have plotted both these graphs for two different channel lengths. Okay, the one on the top is for the shorter channel length. Okay, so clearly you could see that the model that is drawn with the blue colored line, okay, not the dotted line. The dotted lines are by making use of this models. Okay, I've used these two models to draw these dotted lines gain predictions. Okay, but what you could see here is that you could see that the GM times R naught is quite higher when I'm working in the weaker inversion for both the channels. Okay, so if at all if I want to have a higher gain, then should I need to operate my transistor in the weaker inversion? So that would be the question that you might normally have. Okay, but there is one thing that we also have to consider, and that is nothing but the transit frequency. Okay, so generally the transit frequency is defined. I'm just writing down the formula, but you can just find this relation in everywhere in your textbooks or something. Okay, so I'm just directly writing this particular formula. Okay, so this is a transit frequency formula, and clearly you could see that there's a dependency on the gate capacitance. Okay, this CGG is nothing but the, when I take a MOS transistor, we know that there is a metal oxide semiconductor region. Okay, and that imposes a capacitance which we call it as a CGG. Okay, so it is inversely proportional to the value of CGG. Now let us see like how does it impacts our FT. Okay, as you could able to see, this is my graph that has been plotted on the logarithmic scale. Okay, the current graph of the MOSFET, and clearly you could see that the graph shows that the current is actually getting degraded exponentially when we move inside the weaker inversion region. Okay, this means that the GM of this particular MOSFET will also tries to get smaller. Okay, we have already studied the importance of the GM, right? We want this GM to be always large. Now, clearly, we could see that whenever I'm trying to operate in the weaker inversion, the current is stepping down, and due to which the GM, which shares the same relation as that of my ID by just by a scale factor, we know even the GM will also be reducing. Okay, in order to maintain the constant value of GM over ID. In order to have this to be constant, GM over ID, when the current is getting degraded, even the GM also has to get degraded at the same rate in order to ensure that the ratio remains constant. Okay, but in turn, the speed also gets decreased. Now, why the speed of the circuit gets degraded is just because of this relation that I've said. Okay, so when you try to reduce the value of GM to maintain the constant GM over ID in the weaker inversion, we end up having the FT getting reduced. The speed of the circuit gets reduced, and the same is being reflected over here. Okay, so whenever you are operating in the weaker inversion, we know that the GM over ID is high. Okay, and these are the corresponding values of FT that I've plotted over here. Okay, so the value of FT is small, and as you move along this particular axis, you could see that the graph is stepping down its GM over ID. Okay, and clearly when the GM over ID is small, or whenever I'm operating in the stronger inversion, we end up having this value of FT that is higher than compared to the value of FT that I normally get when I operate in the weaker inversion. Okay, now you might wonder like, is it not possible for us to increase the speed in the weaker inversion? Okay, maybe the reason you may think is that if at all, if I'm trying to, because as I said, the ID is basically proportional to the width. Okay, now this means that if I could able to step up the value of the width, then the current can also be stepped up, and due to which what I can do is that I can increase the current so that I can further increase the value of GM in order to maintain the same ratio. Okay, this is a kind of thought process that may come to you. Okay, but here one thing that you have to observe here is that the current is degrading at an exponential rate. Okay, so this means that I have to increase the width exponentially in order to achieve even a small step in the current value. Okay, what happens is that you have to have a very large width in order to achieve a particular value of current in the weaker inversion, in order to achieve a particular value of GM, in order to get a corresponding speed out of the circuit. Okay, there is also one more thing that happens here is that this CGG which I have written down, is also proportional to the width. Okay, so this is again depends on the value of the width. So when you try to increase the current just by increasing the width, what happens is that the value of the CGG is also getting increased. People generally will not work in the weaker inversion. So the main idea is that even though we say that I'm getting a very high intrinsic gain in the weaker inversion, on the other hand, we end up having a very small transit frequency. Okay? The speed of the circuit becomes very small, and due to which there may be few applications wherein they use this weaker inversions. Say, for example, in medical devices, like where you want to conserve the energy of your amplifier. Okay, so anything like a surgery that they do across the heart, what they do is that they try to implant some sort of electronics inside the body, right? And we want this electronic inside the body to consume the power to be as small as possible. So this means that I have to spend a current IQ that is small so that you can increase the lifetime of the device that has been implanted inside our body, right? So generally, there are certain applications where the weaker inversion finds its application, okay? But on the other hand, you cannot expect a speed out of this particular device that has been implanted to our heart just because of the reasoning that I've said here, okay? So we end up having a very small FT, and speed is also not important for such kind of applications. Okay, so for such kind of cases where the speed is not important, whereas the power is so important, then we can operate our device in the weaker inversion. Okay, in the case of a stronger inversion, we end up having a very large transit frequency, but the efficiency of the transistor becomes slow. This means that you have to spend a lot of power to achieve the maximum speed. Okay, say for example, if you are trying to design a processor wherein you are trying to build a kind of amplifier, then you are free to use the stronger inversion. Okay, but there is also one sweet spot which actually lies between the weaker inversion and the stronger inversion, and that region is nothing but our moderate inversion. So in the case of a moderate inversion, we could see that I might not get the frequency or the transit frequency that I normally get in the stronger inversion, but still compromisable value that I can attain in the moderate inversion. And also I cannot attain a high gain that I have got in the weaker inversion, but still the value that I'm getting is also a comparatively a quite good value out of it. Okay, so basically, we always try to fix our transistor to work in the moderate inversion to get the benefit of both these two regions. Okay, and this is becoming quite popular in today's designs. Okay, now what about ID? Okay, so because I have spoken about the current equation that can be applied in the stronger inversion as well as I can apply in the weaker inversion, because in the weaker inversion we know it is exponentially related to our VGS, whereas in the stronger inversion we know it is quadratically related to our VGS. Okay, these are the two things that we know. But what about the current that exists in the moderate inversion? So that we will just see. Basically, there is a requirement that it has to bridge the current equation that I'm getting from both these weaker inversion and the stronger inversion. So I somehow have to bridge it. Okay, so what people did is that the people came up with some sort of compact models. Okay, so people came up with some sort of compact models like EKV. So you can just Google it and search what is this EKV, and there is also advanced compact model, which is the ACM. Okay, so people came up with this kind of compact model in order to create a current expression in the moderate inversion. Okay, so I'm not going to do the derivation of it, but you can use this model. You can just search for this model such that the current equation is defined not only in the moderate inversion, but these models also define the current equation. The same current model can be used in all three different regions. Okay, so even in strong inversion, I can use this current equation, and even in the weaker inversion I can use. Okay, so people came up with some sort of compact model, okay, to define the behavior of the current. But in order to keep this model to be compact, okay, what they did is that they actually kept only few parameters into consideration. Okay, and a few of the parameters like secondary effects are being let out just in order to ensure that the model stays compact. Okay, involving only very few parameters, like our square law, where it involves only very few parameters to define the current. Here again, the compact models were also being designed in such a way they let off few of the considerations, like few of the second order effects are being let off just to keep the model compact. Okay, so because of which, again, when you try to map these two models with the actual circuitry, there will be some sort of deviation of current. Okay, so again, there is a kind of deviation that we end up. Okay, so let me summarize whatever I've said right now. We want a very simple model. This simple model will help us to analyze the trend. So this means like we want this model to show us some direction in order to achieve a particular spec. Okay, we want this model to be simple, but the simple model like square law and the subthreshold current model actually fails to predict the actual current that flows inside the transistor. Okay, so that people end up creating some sort of compact models like EKV and ACM. Okay, again, these models are being built by adding few more extra parameters. Okay, and these parameters has to be extracted from accurate models. Okay, so we have to do some sort of simulations to extract some values of the parameters, and then we can use the current equation that is derived from the EKV model and use the calculation, like hand calculation, we can do it actually. Okay, so still this model helps us to do hand calculation, and even this model, simple model, is also helps us to do some hand calculations. Okay, so whereas on the other side, when I take the accurate model, where the accurate model currently that is in use is one is this BSIM model, which we are using in the GPTK 180 nanometer technology, and also there is also one more model which is I think PTM. Okay, so this model is again an accurate model which actually involves more than 100 parameters. Okay, so it is not just as one or two. Okay, you are being given with hundreds of parameters, and it becomes very hard to do a hand calculation by making use of this accurate model. Even though it can give the actual behavior of the transistor, we can't use it. As a designer, we do not want this accurate model. What we wanted is a model that helps us to do some sort of hand calculation, and also the model is supposed to be simple enough to show some sort of direction. Okay, but when I go to this particular extreme, okay, as my requirement, what I'm losing is that the model is not giving us the actual behavior. Okay, whereas on the other extreme, I've been forced to involve to use more than hundreds of parameters. Okay, so we need some sort of balance across these two extremes, and that is where the compact models were being used. Okay, but again, as I said, this compact models involves very few parameters. Again, we need few more extra parameters to be added, and then we also have to involve some sort of current equations. Okay, so again, we have to work with the current equations and then try to analyze the circuit. Okay, this becomes quite good for people and the researchers, but for us, even adding few more extra current equation will obviously will move away us from the juice of this particular circuit design. Okay, we want to actually grab the essence of this particular circuit design rather than trying to study different current models and then try to adopt them. Okay, so what we are going to discuss under this GM over ID is that we want to have an accurate model. So what I will do is that I use this accurate model to generate some set of charts, okay, or some set of lookup tables, LUTs, so that there is no need to worry about this hundreds of parameters that are involved. Okay, so I'm trying to step down the difficulties that I'm normally getting out of this accurate model by making use of either the chart or the LUTs. Okay, so that I can also don't want to rely on the complex relations. Okay, and but still I can use some sort of simple design process that has been followed in the simple square law model. Okay, so I'm trying to bridge both these extremes, okay, by making use of those charts and LUTs. Clear? So these charts and LUTs are basically derived from the accurate model, and I'm going to use the simple square law model or the subthreshold model, which actually defines the gain or whatever uh, the the transit frequency of the system or any other parameters in order to know the direction at which I have to move on. Okay, so I can combine both these extremes to actually do the designs. Okay, so till now, whatever we have done is that we spoke about the importance of this GM over ID, and then we also have analyzed that there exist three different regions of inversion. Okay, and the corresponding value of GM over ID that I have to have to operate my transistor in a particular inversion region. And later, we spoke about model that we can use as a designer without putting ourselves into learning some new expressions to reflect the current in all three different regions of operation. Okay, so this is what we have seen till now.